All right, so it is 2 o'clock, so I suppose let's start. It's my pleasure to welcome Jeet Sampat, who's going to speak to us about cyclicity preserving operators. Please, Jeet, whenever you'd like to start.
Thank you so much, Ryan. Thanks for giving me the opportunity to give a contributed talk in this amazing conference. I'd like to thank the organizers of the conference for, organizing this. It's very exciting to be a part of something that is very near and dear to me and my research. So, as Ryan mentioned, I'm going to be talking about cyclicity preserving operators. These are operators from one function space into the other that takes cyclic functions and maps them to cyclic functions. So before we get into the main results and the details, I want to try and fix some notation. So for this talk, we'll be fixing a natural number n and pick a domain inside of Cn. Well, not really a domain, just any open set would work. And X is a space of holomorphic functions on that open set D, which happens to be a Banach space and satisfies the following three properties. The first property being the set of polynomials, which I'll denote by a script P, is dense in the space X, dense in the topology of the space. The second property is that all the point evaluations are bounded linear maps for each point in the domain or the open set D. And the third property is that all of the shift operators, so these are the operators Si, which multiply every function f by the variable zi, these operators are bounded linear maps as well. Okay. So pretty standard properties that you would expect from spaces of analytic functions. Some authors like to define a Banach space of analytic functions as a space that satisfies all of these properties. So some examples of these spaces are the Hardy spaces over the polydisk. So Dn, if you haven't seen, is just the Cartesian product of the unit disk. And a function is holomorphic in n variables if it's holomorphic in each of the variables separately. I'm not going to be going into too much detail about several variable complex analysis. So I'm going to skip. I'm going to assume that you guys are aware of holomorphicity and analytic functions in more than one variables. But if you have any specific questions, please stop me and ask me, and I'll try to answer your questions the best I can. Anyway, so one example is the Hardy space on the unit polydisk. We see the Hardy space come up in almost every discussion about function theory. We also have the Dirichlet type spaces that we had seen last week in this conference, which covers many important cases. Here, note that alpha is a real number, and for different values of alpha, we get some interesting spaces. For example, for alpha equal to 0, we get the traditional H2 space, the Hilbert-Hardy space. For alpha equal to 1, we get the traditional Dirichlet space on the unit polydisk. And for alpha equal to -1, we get the Bergman space, which is what this week is about. And for some example of space which doesn't lie on the unit polydisk, we have the Drury-Arzel space, which I guess we'll see when we talk about the Bezout-Sobolev spaces in the conference a few weeks down. And also when we talk about complete big kernels, these are sort of the basis / models for these spaces. So as you can see, these properties cover pretty much, well, I wouldn't say all the interesting spaces, but quite a lot of them. And the general results that I'm going to show will be valid for all of these spaces. A few more definitions. We have cyclic functions. So for all of these spaces, we can define cyclic functions. We have seen these cyclic functions in the past week. but just for the sake of completeness, why don't I define them again? So pick a function f in the space. This function is said to be cyclic if the shift invariant subspace, which is denoted by S of f, which is the closure of polynomial multiples of f. If this closure is equal to x, then the function is said to be cyclic. Essentially, I can approximate any g in x by some polynomial multiple of f, is what it means for f to be cyclic. I should point out that for all of these spaces that I define, which satisfies the three properties above, the polynomial multiples of f belong to the space itself because the shift operator is bounded. So their linear combinations is going to be in the space, right? So all polynomials can be constructed using some composition and linear combination of compositions of these shift operators. So this definition is well defined. Some interesting properties right away. You can check that since the polynomials are dense by the property P1, the constant function 1, which is in the space X because polynomials are in X, is a cyclic function, right? Because the shift invariant subspace of this function is just going to be the set of, it's going to be the closure of the set of polynomials. And because of this fact, you can check that cyclic functions have to be non-zero or non-vanishing, because if they did vanish at a certain point, then all the functions in the shift invariant subspace would vanish at that point because p times f would vanish. So every function in the closure of this set would also vanish. But the function 1 does not vanish anywhere. So it would be a contradiction. But anyway, in the case of the Hardy spaces, it was shown that a function is cyclic if and only if it is outer. We discussed this in the first week, but in case you forgot, outerness just means that the function satisfies this property. The log of the absolute value of f of 0 is equal to the integral of the log absolute value of f star. So absolute value of f star is just the boundary function of absolute value of f. We discussed that radial limits exist almost everywhere on the boundary. That applies to the n variable case as well. And whenever this condition holds, we say that the function f is an outer function. So when n is equal to 1, a complete characterization of cyclic functions has been known for the Hardy space. But for almost every other exotic space, the classification is completely unknown. And one of the most common ways of obtaining examples of cyclic functions in different spaces is through mapping cyclic functions from one space into the other. So what you would do is, let's say you have a good set of examples for cyclic functions in a space X. Why don't I try to find linear operators that take cyclic functions from X onto cyclic functions on Y? That way I can come up with some examples of cyclic functions in the space Y, which I had no idea about. And from all the examples that I could find, I noticed a pattern, which was the fact that all of these operators look like composition operators. So it's natural to ask the question, do all of these operators satisfy this property? So a result of Mashreghi and Ransford shows that this is true for the Hardy spaces over the unit disk. So we have this following theorem. So if P is between 0 and infinity, and T is an operator that maps the Hardy space inside of the space of holomorphic functions on the unit disk, such that T, the image of every outer function G, is a non-vanishing function, then you have analytic maps phi and psi such that T of f is the following weighted composition operator. So if instead of holomorphic functions on D, if I map to a space Y, on which cyclic functions make sense, then as cyclic functions would be non-vanishing, the property that T maps cyclic functions to cyclic functions would be a specific case of the property in this theorem. So the meta theorem in that case would be, can you find examples of other spaces for which this property holds true? And that's what got me thinking about it, about this particular problem. And before I move on to that, I want to note that in the same paper of Mashahidi and Ransford, they prove a version of this theorem for more general spaces, X, which lie in the space of holomorphic functions on the unit disk. And it had some extra properties that I don't want to get into too much detail. But the most important thing to note about this particular theorem is that the continuity of T is not assumed. So nowhere in the statement of the theorem do we mention that T is a bounded linear operator. It just happens to be bounded automatically. It turns out that in order to prove the same theorem for more than one variables, you kind of have to assume the boundedness of the operator. Although we do get more general examples of spaces for which this can hold true if you assume continuity. So with that being said, I'll move on to a preliminary result, which enables us to prove the main theorem. So going back to the original notation that I discussed, suppose that X is a space of holomorphic functions on D, which was an open set in Cn, and it satisfies these properties P1 to P3. So polynomials are dense, point evaluations are bounded, and the shift operators are bounded. Then it's not too difficult to see that these functions, exponential of w dot z, so the dot represents the dot product in Cn. All of these functions would belong to the space X. Just you could take the Taylor series of e to the w dot z and approximate that Taylor series absolutely in the norm of X. So that would show that these functions belong to the space X and that these functions are cyclic. So this is not completely trivial, but it's also not difficult to check why this is the case, because you could use the same Taylor series approximation for the inverse of this function, which is e to the negative w dot z. And using the Taylor series of this particular function, you could come up with a sequence of polynomials p such that you can approximate the constant function 1, which would imply that the function is cyclic, because the constant function 1 belongs to the shift invariant subspace of this function, and hence all polynomials belong to the shift invariant subspace. And in turn, the function will become cyclic. So with that in mind, the statement of the preliminary result goes as follows. So if I have a bounded linear functional on X such that it sends all of these exponential functions to some non-zero number for each w in Cn, then you can identify this linear functional as acting almost like a point evaluation, but with a weight attached to it. So all of these lambdas would look like lambda p is equal to a times evaluation at the point B for some point B in the right hard spectrum of the shift operators. I'll get to the definition of that in a bit, but the main idea is that all of these linear functionals, they look like point evaluations when restricted to the set of polynomials. And the right hard spectrum is the following set. So if you take the resolvent set, which is the set of all lambdas in Cn, such that you have a sequence of operators ai on X, such that this condition is this condition is true, then the complement of this resolvent set is going to be the right hard spectrum, which is a compact set, which is important because the important thing to note is that this point B cannot be too arbitrary, in the sense it's not too far away from the open set itself. Ideally, we would want the point B to lie inside of D because we have the nice point evaluations are bounded assumption, and we would want to use that in order to identify these linear functions properly. And the right hard spectrum doesn't really tell you all that much about what the point is doing, because it could still be a very abstract part of the boundary that we might not be able to properly understand. So we can cheat our way into fixing that. Although I would like to give an example where you can't really expect the point to be in the open set itself. So let's go to the one variable case and pick an alpha greater than 1, so that the Dirichlet type space with factor alpha lies inside the is a subalgebra of the algebra uh, of the disk algebra. So if I take a point which is in the closure, actually in the boundary of the disk, not just the closure, if it is the boundary of the disk, then the point evaluation functional is bounded and satisfies this property. So we proved that there exists a space for which this point B does not lie in the domain of functions. But since the space is a subalgebra of the disk algebra, we can extend all of these functions onto the boundary, or at least define them, maybe not holomorphically, but we can at least define them via limits. So that's where the idea of maximal domains comes in. So this is going to be something that is going to be the maximal set on which functions in the space X could be defined in certain sense. So the maximality would be in regard to some condition, which we'll get to. So for the space X, we define the maximal domain D hat to be the set of all points W, such that the restriction of the point evaluation at W onto the set of polynomials has a bounded linear extension to X. Okay, so clearly the open set D is going to be a subset of the maximal domain. But using the theorem above, you could also show that the maximal domain is inside the right-hand spectrum of the shift operators. And we haven't really done any kind of math. This is just definitions working the way through. The point is that in the statement of the theorem now, you could replace B lying inside the right-hand spectrum to B lies inside the maximal domain. And you can replace this thing to just say that lambda is a weighted point evaluation for all functions in X hat, which I'm going to define in a bit. But the idea is you can simplify the statement of the theorem a little bit to include the maximal domains. In the case of the Hardy spaces, the maximal domain is equal to the domain itself. So you cannot extend the functions any further, at least not in this way. For Dirichlet spaces, when alpha is less than or equal to 1, you can again show that the maximal domains have to be equal to the unit polydisk. But when alpha is greater than 1, based on the example I showed above, it shouldn't be a big surprise to note that the maximal domain has to be the whole closure of the unit polydisk. So a natural question is, can we extend all functions in X to D hat? And the answer to that is yes. So it's a easy check to, well, let's say we have a function f in X, and we pick polynomials in X that converge to F. Then we can define f hat to be the limit of the point evaluation at Z for each Z inside the maximal domain. And you can show that this space X hat satisfies P1 through P3, but actually a variant of P2, which just says that not only are the point evaluations bounded, but if you have a point Z such that the point evaluation restricted to the polynomials at Z extends to a bounded linear map, then the point Z has to be inside of the maximal domain. So this kind of justifies that in this theorem, I could replace B lies in the right-hand spectrum with B lies in D hat, and this condition over here to lambda f is equal to a times f of b for all functions. Okay. So the main point of this section was to show that the space x hat, which is just the collection of f hat that I defined above, can be identified with x with an isometric isomorphism. X hat satisfies P1, the augmented P2 property, and P3. And also f is cyclic if and only if f hat is cyclic in x hat, because polynomials are going to be preserved under this identification anyway. So you can define polynomial functions, etc., and check that cyclic functions are the same for both of these spaces. So we might as well work with a space on which the functions are defined on the maximal possible domain, maximality being with respect to extensions of point evaluations at certain points. Okay, so the main result that you can show using the theorem I proved above is the following. So if I take x hat as above, which is the space defined on the maximal domain, and if I take y to be a topological vector space of functions on some set E, doesn't have to be the complex thing, it could just be any random set, with the property that the point evaluations for functions on the set E are bounded in Y as a functional on Y. I guess I should say continuous because it's a topological vector space and not a normed space. So Y is a topological vector space with the property that point evaluations are continuous linear maps, and X hat is just as above. And I have a continuous operator T from X to Y. Then the following two conditions are equivalent. First is the image of the exponential map is non-vanishing for all W in Cn. And the second condition is that there exists appropriate maps A in Y, which is a non-vanishing function, and a map B from the domain of Y onto the domain of D, the domain of X hat, such that T is a weighted composition operator. And it should be noted that these A's and these B's can be identified by the image of T onto certain functions in X. So this sort of covers the cyclicity preserving operators because all of these functions e to the w dot z are cyclic. So if I had the condition T of f is cyclic for all cyclic f, then I would just have to show that, well, e to the w dot z is cyclic, which I know. So the condition, so the above condition is going to be satisfied if this condition is satisfied, right? Because the cyclic functions over here on the image space are going to be non-vanishing themselves. Although one thing to note is that the reverse inclusion is not going to be true in general for cyclicity preserving operators, because not all weighted composition operators preserve cyclicity in general. But in the case of the Hardy spaces, so if we assume y to be equal to a Hardy space for some value of q and some different number of variables, then 2 implies 1 is going to automatically hold true in the above theorem if we replace the exponentials with cyclicity condition. So I guess that answers the question completely in the case of Hardy spaces, that an operator preserves cyclicity if and only if it preserves, if and only if it is a weighted composition operator, a bounded weighted composition operator. Now, one last thing I would like to add, which would be like a nice example and a good question that I couldn't figure out the answer of, is that we could replace the cyclicity condition with outer condition. So we could consider T from X to Y if both of these are Hardy spaces in some dimensions. If T has the property such that TF is outer whenever F is outer, can we classify all of these operators? So just like we did with the cyclicity case, e to the w dot z can be shown to be an outer function as well. So all outer preserving functions are going to be bounded weighted composition operators. but is the reverse direction true as well? And the answer to that is no. So if I define this operator from H2 of the bidisk onto HQ of the unit disk, where Q is any number less than 1/2, then the operator that I defined over here that takes f to f of 1 plus z over 2, comma 1 plus z over 2, it does not preserve outer functions. So here's the explicit example. If I take this f, which is outer, then its image, which is this function here, can be checked that it's not an outer function. So the final question that I would like to leave you guys with is can we characterize all outer preserving operators? Because I feel like that could tell you an important difference between the outer functions and the cyclic functions in the case of Hardy spaces. And also, it would be interesting to determine what properties on the boundary for a function would determine outerness as well. Because in order to check the condition of weighted composition operators preserving outer functions, you would have to worry a little bit about the growth of the function on the boundary. So I think that's all I had prepared for this talk. Sorry it was a little quick, but thank you for your attention, and I'm happy to answer any questions you might have.
Let's thank the speaker. Does anyone have any questions? No? All right. If not, thank you very much for the fantastic talk. And yes. So I will stop the